This video covers section 4.2, measuring evidence with p-values. So Paul the octopus is going to be the topic of the first example that we're going to do in class today. So if you didn't attend class, I suggest taking a look at this video and seeing how Paul made his choices. But Paul the octopus was an octopus, obviously, who lived in a German aquarium. And between 2008 and 2010, he was asked to predict the winner of 14 international soccer matches. Now, this was done by putting snacks in containers. There were 2 snacks, one with the flag of each of the competing teams, and whichever container he chose for his snack first was the team that he was believed to have been chosen as the winner. So using this method, Paul correctly picked the winner in 12 of the 14 matches. And so what we're going to consider today is deciding how strong is the evidence that Paul's success can be attributed to something other than just guessing. As we saw in last week's class, the first step in hypothesis testing is always to formulate our hypotheses. And to do this, we use the research question and figure out what the null and alternative hypotheses are. Generally, the research question is formulated something like this: how strong is the evidence that, and whatever comes next is the alternative hypothesis, remember. So in our example, in this situation, the research question is, how strong is the evidence that Paul's success can be attributed to something other than just guessing? We're going to write the hypotheses. Now, first of all, I need to figure out what the parameter is, because I always write hypotheses about the population parameter. For each of the matches, they recorded whether Paul's pick was correct or incorrect. So that's one categorical variable, which means that my parameter is a single proportion, p, and it represents Paul's ability to correctly predict the winner of international soccer matches. Now I'm trying to decide how strong the evidence is to support the alternative. So the alternative is that Paul's successes can be attributed to something other than just guessing. So I'll shorthand that. Paul's ability was better than just guessing, which would mean that his ability to predict the winner would be more than 50%. And that means that the null hypothesis then must be that the proportion p is equal to 0.5, or that Paul was just guessing. Now, once we have our hypotheses, we're going to need to find a sample statistic that will serve as evidence against the null hypothesis. And since our hypotheses are about the population mean, the best estimate of that from the sample is the sample mean, p hat, which is 12 divided by 14. 12 correct picks out of 14 total is 0.857. Now we're going to need a way to measure the strength of this evidence. So we're going to use something called the p-value. Is the probability of observing a sample statistic as far or farther from the hypothesized value. And by the hypothesized value, what I mean is the null value in the direction of the alternative if the null hypothesis is true. This measures how consistent the sample statistic is with the null hypothesis. So basically, if I have a very small p-value, what it's telling me is that if the null hypothesis were true, there's very small chance that I would see a sample like mine. My sample is not consistent with the null hypothesis. On the other hand, if I see a large p-value, it's telling me that this is a sample statistic that would be likely to occur by chance if the null hypothesis is true. And so the sample is consistent with the null hypothesis when the p-value is large. So this is the opposite of how we're used to thinking about things. We're used to thinking about things that are big as being strong. But when it comes to p-values, smaller p-values give stronger evidence against the null hypothesis. So you have to think like little and strong, like Mighty Mouse. So the next question we'd like to figure out is, okay, so we know what the p-value is measuring now, but how do we find it? So the first thing we need to do in order to find the p-value is generate a randomization distribution. The randomization distribution shows statistics that might occur due to chance if the null hypothesis is actually true. Because it's showing statistics that might occur if the null hypothesis is true, it's always going to be centered around the null hypothesis. And the way that we are going to generate this distribution is using StatKey. In StatKey, at the right side, there is an entire section of randomization hypothesis tests, and that we can choose the type of parameter that we have hypotheses about over there, and it'll bring us into the correct applet. So we're going to take a look in a second at how we would do that for this particular situation. Since our hypotheses were about a proportion, I chose the randomization test for a proportion, and then I needed to come in. I changed the data to reflect the original sample using the Edit Data button. And then I generated 5,001 samples. Notice that I also need to make sure that the hypothesis, the null hypothesis, is set correctly. And it gives me a distribution of results that are consistent with the null hypothesis. So this is showing me if Paul were to randomly guess for 14 games, what kinds of results would I expect to see for the proportion that he guessed correctly? Now the next step after this distribution has been simulated is to decide which tail to use to find the p-value by looking at the alternative hypothesis. In our case, our alternative hypothesis was that p is greater than 0.05. So I'm going to use a right-tailed test. So in StatKey, we choose the tail that we want. Here I checked the right tail box. And what happens is that StatKey will automatically put in a right tail, and it will show us the value that cuts off the upper 2.5% of the distribution. This is not the p-value. The p-value is the chance of seeing our observed sample statistic, or something more extreme, if the null hypothesis is true. This isn't telling us anything about the chance of seeing the observed sample statistic. This is telling us about 0.786, which is not our sample statistic. So before we have the p-value, we're going to have to move this cutoff. We're going to start the tail at the sample statistic from the original sample, which remember was 12 out of 14 or 0.057. So I'm going to come back into StatKey and I'm changing the sample statistic to 0.057. Once I've done that, StatKey is calculating the p-value for me. The way that it's doing it is it's taking the number of dots in the tail and it's dividing it by the number of samples that I generated. This p-value is the proportion of the dots that are in the tail of the randomization distribution. And it's a good way of measuring the chance, or the proportion of the times I'd expect to see a sample statistic like ours, 0.857, or more supporting the alternative, even bigger, if the null hypothesis is true. There's our p-value. So in the context of this example, we want to know what is the correct interpretation of the p-value. The correct interpretation is C. The p-value measures the probability that Paul would be correct at least 12 out of 14 times. There's our sample statistic. If he's randomly guessing, if the null hypothesis is true. Once we have a p-value, we can start to think about how strong the evidence is against the null in support of the alternative by comparing the p-value to this sort of shades of gray scale. Now remember, the smaller the p-value is, the stronger the evidence is against the null and in support of the alternative. And if we have something down below about 0.01, we start to say that the evidence is very strong. On the other hand, large values, those that are above 0.10, are very weak evidence against the null hypothesis and in support of the alternative. And we have all the shades of gray in between. Now, in our situation, we found the p-value was 0.005. So that falls down here in the very strong range. So there is very strong evidence that Paul's success is due to something other than just guessing. So if we don't think Paul was just guessing, what are some other possible explanations for his success? I'm sure you can come up with a few. Maybe they put a different snack in the two boxes and someone who knew something about soccer was the one who was setting the thing up. Maybe he liked certain colors of flags better. But my guess is that he was mostly asked to pick the winner of matches that involved Germany. And Germany had a very good soccer team during this time. He usually picked Germany, so maybe they did something to entice him to pick Germany. Who knows? Maybe they fed him his snack out of a container with a German flag on it every day, and then, you know, popped in the other one just for when there was a match coming up. Who knows? But there's something going on. Okay, so we're going to look at one more example of how to find a p-value. This example looks at a study in which 11 patients were recruited, and they were investigating whether on average inflammation differs before and after massage therapy. For each participant, the researcher recorded the change in inflammation levels between before massage minus after massage. So we've got inflammation levels measured quantitatively and then a difference calculated. So that difference is going to be one quantitative variable, which means that the parameter that we're interested in here is a single mean mu, the mean difference in massage level before and after. And I'll just mention also that since it was before minus after, a positive value of this difference would indicate that inflammation is lower after massage. And a negative value would indicate that inflammation was higher after massage. And of course, a difference of 0 would indicate that it was the same before and after massage. Now, the research question we're going to answer is, how strong is the evidence that, on average, inflammation differs before and after massage therapy? Take a few minutes and use the 4.2 handout to try working through some of this yourself if you can, and then come on back in and start watching the video. Okay, so we're going to start off first of all with the hypotheses that will be tested. Again, the parameter of interest is the population mean mu, and we know that our hypotheses are going to always be written about that population mean. The null is always going to be that the mean is equal to a value, and the alternative is going to be that it's somehow different from that value. So we want to know how strong is the evidence that on average inflammation differs before and after massage. Remember, we're always trying to decide how strong the evidence is to support the alternative. So this is that it differs, which would mean that the null is that the inflammation levels are the same. Now we said that if the inflammation levels were the same, that the mean difference would be 0. And now we're looking to see if it differs. It doesn't indicate in which direction. So without an indication of direction, we're going to do a not equal to sign, so that we have the ability to pick up a difference whether massage decreases or increases the inflammation. Now here's the randomization that was simulated using 1,000 samples this time. Now normally I would do more than that, but once you have 5,000 samples on there, you can't count the dots very easily. So for these purposes, we're going to put it on there with just 1,000 samples. So remember, the next thing I want to do after I've got the randomization distribution that's centered around the null value is I'm going to figure out the observed sample statistic. Now this always comes from the original sample. Since our hypotheses are about a single mean, my best estimate of the population mean is the sample mean, which is 1.3. And again, I'm taking that from my original sample. Now note that since my alternative hypothesis was that the mean is not equal to 0, this is what we call a two-tailed test. When we want to find the p-value for a two-tailed test, we find the proportion of dots in the tail where we find the sample statistic, and then the p-value is twice that proportion. So let me show you in this example how we do that. So here I've got my sample statistic, x bar is 1.3. For my two-tailed hypothesis test, I'm finding that value and I'm using that as the cutoff. And I'm going to count the number of dots that are out in this tail. Because remember, the p-value, I'm thinking about the proportion of the time I'd have a result like this. So out here there are 28 dots out of 1,000 total samples. Here's my number of samples. So the p-value, because it's a two-tailed test, my p-value is going to be equal to 2 times the proportion of the dots that are in the tail. So that's going to give me a p-value of 0.056. Now I can use this p-value to think about how strong the evidence is that inflammation levels are different on average after massage. 0.56 is somewhere around here. So the evidence is moderately strong. There is moderately strong evidence. That inflammation levels differ before and after massage. Is it possible to make a cause and effect conclusion in this study that massage changed elevation levels? So remember, when we want to make a cause and effect conclusion, what we would need to see is we would need an experiment with random assignment. In this case, we do not have an experiment with random assignment, so the answer to this question would be no.